Today we'll show how to compute the net electric field for charges spread out uniformly on spheres. Just to be clear, we are going to distinguish situations where the sphere is hollow, we'll call such spheres spherical shells, from situations where the sphere is not hollow. We'll refer to such a sphere as either a solid sphere or simply a sphere. It's important that in problems involving charged spheres, we determine early on which of these cases we are dealing with. Let's remind ourselves once again the recipe for carrying out this type of calculation. First, we're going to divide our charged sphere into pieces. The type of piece that we'll choose will depend on the situation, and we'll discuss that as we go along. Now, in the cases that we'll consider, it will turn out we will already have in hand math expressions for the electric field of a typical piece. So then what we'll be able to do is use those expressions and sum up the electric fields of all the pieces that comprise the spheres that we're looking at. Now again, the summing process can be done analytically or numerically using a computer. In this lecture, we're going to show the results from computer calculations and just simply state but not derive the analytical results. We're going to start with the situation of a spherical shell, and we'll do demonstrations of numerical calculations which will allow us to visualize the calculation process. Now, it will be important for us to pay attention to whether the observation location that we're focusing on is outside the spherical shell or inside the spherical shell. So here we show a spherical shell in red with charge spread uniformly on the surface of the shell. Here we'll assume the charge is positive. Let's first consider the case where the observation location is outside the shell. Step one is to divide the spherical shell into pieces, which in this case we'll choose to be charged rings. In the numerical calculation, we decide how many pieces we'll want to work with. So in general, the more pieces we choose, the more refined our calculation will be. Now, step two would be to write down the expression for the electric field of a typical ring. Here we can use our earlier result for the electric field of a ring on the ring's symmetry axis. It will turn out that for any observation location that we choose, we will always be able to choose a set of rings that cover the shell and share the same symmetry axis. Also, let's remember that on the symmetry axis, the E field of each ring is parallel to that axis. Now, we can compute the electric field for each ring and add up all the contributions. In the program, we do this one ring at a time. The E field contribution of the piece we're focused on at the moment is shown by the blue arrow. The red arrow gives the sum of all the electric fields we've calculated so far. As we progress through all the rings that cover the sphere, we get our final result. The red arrow shows the total E field due to the uniformly charged spherical shell at an observation location outside the shell. Let's repeat all this for an observation location positioned inside the uniformly charged spherical shell. The procedure is the same. Divide the shell into rings, use the expression for the electric field of a ring for observation locations on the symmetry axis, and sum up the contribution. The red arrow again gives the sum of all the electric field contributions due to the rings we've calculated so far. In this case, though, we notice something quite interesting, that at the end of our calculation, the red arrow is essentially 0, meaning the net E field inside a uniformly charged spherical shell is 0. This result is general. Regardless of which observation location we would choose inside, we would find the electric field at that location is 0. Now, it's possible to do all these cases analytically. That is, compute the net E field of a uniformly charged spherical shell. We won't do that here, but we will state the final results. So let's consider a spherical shell with a total charge, capital Q, spread uniformly on the surface. Let's take the shell's radius to be capital R, and let's calculate the electric field due to the uniformly charged spherical shell at an observation location outside the shell indicated by the position vector R. Outside the shell means the magnitude of the vector R is greater than capital R. Then, in that case, the analytic result for the electric field of the charged shell is easy to state. It's the point charge formula, where vector R measures where the observation location is with respect to the center of the shell. In other words, for observation locations outside the shell, we can think of all the shell's charge, capital Q, as being placed at the center of the shell, and then we can compute the electric field due to that shell using the point charge formula. Now, instead, if the observation location is inside the shell, that is, the magnitude of vector R is less than the radius of the shell, then in that case, the analytic result for the electric field of the shell is even easier to state. It's simply 0. These results for the net electric field of a uniformly charged shell are quite useful, and we'll return to them repeatedly in this course. Let's now consider the case of a solid sphere of radius capital R, where a total charge of capital Q is spread throughout the entire volume. Let's assume Q is positive. We're going to break the sphere up into pieces, and it's quite useful to choose those pieces as a nested set of concentric spherical shells. Now, for observation locations outside the sphere, that is, for the magnitude of the vector R greater than capital R, the location is outside of all the shells which share the same common center. So the net electric field of the solid sphere is given by the point charge expression, where capital Q is the total charge and vector R locates the observation location with respect to the center of the solid sphere. The case for the observation location inside the solid sphere is different. We can still use the idea that the solid sphere consists of nested concentric shells. Now, the E field contribution from the charged shells shown in gray here is 0 at the observation location, because the observation location shown here is inside those shells, and as we just discussed, the E field of a charged shell is 0 inside that shell. So we can ignore all the gray shells, that is, ignore all shells with radii larger than the magnitude of vector R. However, the observation location is outside the shells shown in red. Those shells altogether have a total charge of small q, which is a fraction of the total charge capital Q. And the shells shown in red contribute a non-zero net electric field. But we can calculate that easily. We just use the point charge formula for these shells because, as we just discussed, that's what one does for the E field outside a charged shell. Now, as before, the vector R locates the observation location with respect to the center of the shells, which is the same center for all the shells. However, in the point charge formula, the charge we use is small q, so we need to figure out that in terms of known quantities. Now, this full sphere is uniformly charged, which means the ratio of the total charge, capital Q, to the volume of the full sphere is a constant. That volume of the sphere is 4/3 pi times capital R cubed. And that ratio must be equal to the ratio of the charge small q to the total volume of the smaller sphere shown in red, 4/3 pi times the magnitude of vector r cubed. We can solve this for small q in terms of known quantities. We can then substitute that in to get our final result for observation locations inside the uniformly charged solid sphere. That's it for now. In our next lecture, we will begin to discuss the concept of electric potential.